So just if you can, just let me, give me a comment or something. Just let me know that everything is running okay. You can hear me and everything's um, streaming seemingly fine. So today's video, what I'm mostly talking about today is read mapping. Um, so read mapping. Sorry, let me back up. So what we've done up to this point is we've built a transcriptome. And so what's nice about building a transcriptome is that we can generate a set of genes for any species. It doesn't have to be a model organism. We've been dealing with mouse just because there's so much data already available that it's just kind of easy to work with. But the solid majority of species do not have information as clear as mouse data. So we build assemblies, either genome assemblies or transcriptome assemblies, when we don't know what our data looks like, when we don't know what genes are present, and when they're not already annotated. So if we remember when we just built an assembly for um, a single tissue, it didn't really matter if it was liver or if it were um, kidney. We should still see about 10 to 12,000 genes plus or minus expressed. So if we wanted to get every single gene expressed in an individual or expressed in a species, then we would take samples and assemble all tissues. So we would get tissue samples from the liver, from the spleen, from the kidney, from the intestine, from muscle, from brain, from everything to try to get up to that 20 to 22,000 genes for a given species. But what's already nice about the mouse is it's already done, and it's been done 12.5 times over. So we don't have to build new assemblies anytime that we get RNA data or genome data from the mouse because it's already readily available. And so, for example, so I'm in data. Um, I added a new directory to this global data directory where we had our SwissProt database. I'm also keeping one where I have the mouse CDSs. And so the mouse CDSs these are the annotated genes of the mouse. Um, the only file that really matters in here is just the mouse CDS.fasta. Um, I'll talk about the other stuff here in a minute, but this mouse CDS.fasta, again, these are all of the gene sequences for at least protein coding genes. Um, so let's see. I think I have, let me grep this out. So I'm going to count how many genes are actually present or how many sequences are present in this file. So mouse CDS. So we have 68,000 different transcripts already annotated in this file, and they are in a FASTA format, right? So these are gene sequences. This is just ensemble nomenclature. There's an ensemble gene ID, an ensemble transcript ID, and then a general gene ID, or just some gene description that's a little bit more easy to recognize, easy to work with. But we'll see in this file, let's see, I'm going to grep up this specific gene. And see, 1, 2, 3, 4, 5 different transcript variants are present in this file. Recognize they all have the same ensemble gene ID and gene name, but there's a different transcript, and it's just caused by this alternative splicing. So let me list that real quick. And we're going to find that gene, right? So here's probably a full transcript that includes every single exon. I want to search on this one. Let's see, but here's another transcript variant that's much shorter, so only a handful of exons are actually expressed out of this one. Um, there's another one with even fewer exons expressed, um, and there should be a couple more. So there's another one that includes the whatever, includes the start codon and a couple of, but whatever. Point being is that even though we have 60,000 different transcripts, but they should still all relate to 20,000 genes. And I can go ahead and count that real quick. By doing so, I'm going to grep on the OpenCaret. And now cut, since cut lets me delimit, I'm going to supply a delimiter as the pipe. And that should at least separate stuff out. Cut on the pipe dash F1. That should give me the gene name. Yeah, so that gives me the gene name. Sort all these things out because they're not in nice sort ordered. Just grab the unique ones. And I'm going to count them. And hopefully 44 more. Somehow they became more. Unique, sort unique. I'm not going to worry that much about it. But somehow that became more. Whatever. I don't have time to fix it. I don't have time to really try to figure out what happened there. Anyways, this is, nonetheless, if I'm going back, this is our reference. This mouse CBS stuff is our reference. And we've sequenced our RNA. And again, instead of assembling its stuff, we can map each read to the known transcripts. So we can basically kind of do a blast search, in some way do a blast search. This sequence, say this read, this 150 base pairs seems to be more similar from the very 3' end of, COX11 or whatever. We can map these reads out to figure out what gene they're specifically derived from. And whenever we're dealing with transcripts, there are two major things that we care about in a transcript. We're like, what gene is there and how is it expressed? The second question is more or less what we're addressing today. So we've already kind of played around with what genes are there, but now we're kind of staying in the same world. We're going to keep using the data that we've already generated and cleaned up. That's why I was kind of so persistent about getting y'all to do it. So you have these clean reads because we're going to use them again. We're going to use them again to measure expression. And the end goal of all of this, remember, the liver is expressing a different set of genes than the kidney. So what we're going to do is we're going to measure expression from all of these several thousand genes and figure out which ones are differentially expressed. What's more expressed in the liver versus the kidney? What's more present in the kidney than what's in the liver, et cetera, et cetera. And so to do that, we want to map to one reference. We don't want to assemble a liver assembly and map kidney genes or map kidney reads to the liver. It doesn't make any sense. We want to map everything to one reference. And thankfully, Ensembl already more or less makes this reference for us. There are 12.5 good mappers. When I say the mappers, these are going to tell us which gene these reads came from, or how many reads are each gene produced. So there are a handful of really good ones. BWA is probably my favorite at this point, but some of the older ones, Bowtie is still useful. It has its uses. I think Star is another mapper that's getting a little bit more attention. I do like Star a lot. Because there are some issues with mapping reads. And one of those issues is if a read maps to more than one region, where did it come from? And so that's kind of a tough question to answer, and it's still kind of a tough question to answer, but Star kind of handles that a little bit. I think it handles that a little bit better than some of the others. It doesn't mean they don't handle it. I just have this subjective idea that Star deals with this a little bit better. So originally, like the OG mapper was BLAST. So back when these data were being produced and we're trying to figure out where these reads come from, the original process to do that was BLAST, right? But BLAST takes forever. And so around 2007 plus, you start to see the development and publishing of really good, fast mappers. Again, BLAST is slow, and BLAST is slow because how it searches is just slow in itself. So um, uh, better developers have produced and produced some really amazing mappers. We're not going to directly interact with a specific mapper this week. Um, Instead, we're going to work with a software suite that calls a mapper. Um, so in this case, I've set this up so that our wrapper programs are going to mess with a bowtie mapper. And bowtie, for our intents and purposes, this is fine for what we're doing, fine for practicing. And bowtie is kind of my traditional approach. But if I were to change what I were doing, I'd probably change my mapper from bowtie to star, and see if that works any better. But anyways, let's see. So let's see. I'm frozen. So I'm going to go back to my reads. So my reads are my home, test mouse, data, seek, right? So I did change this a little bit. My main reads are in my assemble. So this is where my clean reads are, my SSR, my raw files are at. I got rid of the unpaired stuff. I'm not going to use them, so they just take up space. So I got rid of the unpaired reads. I'm just going to work with the clean reads, right? So we've already polished these things out. We've gotten rid of adapters. The clean reads are what we would actually want to interact with. So I'm going to actually run this pipeline or run this script or run this command in another folder called exp. Either way, all I have to do, I can be in another directory and still call those files. I just have to tell the program where those files are located at. I'm going to open up the TBox. So the program that we're working, what we actually call is RSIM. And RSIM is this pretty big suite that contains a lot of tools that assist in not only just mapping reads. So RSIM is going to call bowtie to map reads, but then it's also going to count the number of reads that map to each gene. That's its overall goal. I think there are two major ways to measure gene expression. One of those is to map our reads directly to our genome, and then use, say, our GTF file, our coordinate information for all of our exon and CDS information, and use that to reference for where our genes came from or where our reads came from, what genes are expressing the most reads, that way. So mapping to a reference genome and then using the coordinates to understand what genes those reads came from. The alternative is what I'm doing today, is mapping reads directly to a gene set. There's probably some arguments of what's better or what's worse. Not going to worry about it today. Mapping to a genome does take a little bit longer. It's not substantially longer, but it does take a little bit longer, and it takes a few more program suites. So it does this one is a little more streamlined. We can do everything in one step if we just measure reads, measure expression from a known list of genes. And I think it's easier to use and it's a little bit easier to explain. And I think we'll have less headaches because we have fewer programs to work with. The fewer programs we have to work with, the fewer problems that we can run into. So we're going to use this RSIM suite. And I've already used RSIM to prepare our reads, or sorry, to prepare our genes to be mapped to. So all of those additional files in that mouse CDS folder, all of those additional files are produced by RSIM. It's just something they're files that have to be produced because those files are what's going to be searched through for similarity to our reads. And those files are produced in a way, they're manipulated in a way to make searching much, much faster than doing like a raw search, say a brute force algorithm to look through which reads um, came from which. Oh boy, I timed out. Hold on. Am I still streaming? Okay, okay. Just give me a couple of minutes. I had a problem, so give me a minute or two. What is going on? So I'm gonna kill this now. But I'll be back in I'll be back as soon as I can fix the problem. Give me 2 seconds.